Hello AP Chem students and welcome to topic 6.7, bond enthalpies. The learning objective for today is 6.7.a, calculate the enthalpy change of a reaction based on the average bond energies of bonds broken and formed in the reaction. So we looked in the last topic at the amount of energy that can be generated by a reaction or absorbed by a reaction, right? And so that was a delta H that's usually denoted at the end of the reaction itself. What we're going to look at over the next few topics is different ways that you can actually derive that energy for the overall reaction. So the way we're going to look at today is bond energy. So each bond that is broken and formed during a chemical reaction is described by bond enthalpy, also called bond energy or bond dissociation energy, which is specifically the amount of energy that is required to break 1 mole of covalent bonds between two atoms in a molecule in the gas phase. So that's how they measure it. Not necessarily super important for you to understand how that happens, but just want you to know where it comes from. Enthalpies for bonds breaking have a positive sign, as breaking bonds requires energy. Conversely, bond formation has a negative sign since energy is released. And so this is really important for you to know. Breaking bonds requires energy, forming bonds releases energy, and that is going to be an important theme throughout the whole course, but especially for the rest of this unit. So here's a little graphic for that. In order to break bonds, energy has to come in, and so then that is an endothermic process. And in order to, and when bonds are formed, energy is released, and therefore that is an exothermic process. So when you undergo a reaction, you have an endothermic and an exothermic process both happening if you have both bonds breaking and bond forming. But it's the comparison between the amounts of energy that's required and energy that's released that tells you if the overall reaction is endothermic or exothermic, and that's what we're going to look at now. So if we compare the energy of the bonds broken to bonds formed, we can calculate the enthalpy of the reaction like I was just mentioning, and this is the equation that we do for that. This is the only time in thermodynamics that we do reactants minus products. It is normally products minus reactants, but we flip it in this case. I actually prefer to think of it in this way. I like to think of it as bonds broken minus bonds formed. That just works a little bit better in my head. Then I don't have to think about, wait, is this one where reactants and products flip? If you just kind of call it something different, kind of helps set it aside in your brain. So bonds broken minus bonds formed. So delta H in this case represents enthalpy. BE is bond energy. Okay, so there you go. Note that this equation is not on the equation sheet, so you do need to memorize it. So again, bonds broken minus bonds formed. When using this equation to calculate a reaction enthalpy, it is very helpful to draw Lewis structures of the reactants and the products to account for the number of each type of bond, because you need to know exactly how many of each individual type of bond is present in the reactants and in the products. We can also qualitatively say if the sum of the bonds of the reactants or the sum of the bonds of the products is greater by considering the sign for the delta H for the reaction. So we're going to look at both of those cases here. So remember from topic 2.2 that bond order, bond length, and bond energy are all related. So for example, if you have a carbon-carbon single bond, a carbon-carbon double bond, and a carbon-carbon triple bond with a bond order of single, double, triple, so bond order 1, 2, and 3, you can see that the bond energy increases as you go from a bond order of 1 to a bond order of 2 to a bond order of 3. Now, notice it's not exactly a direct correlation, right? We don't double the bond energy to go from single to double and then double to triple, but it does increase, right? So as you as you have more bonds, your bond energy gets higher, which we typically say is the bond is stronger, and your bond length gets shorter. So that's a review. So to refresh, single bonds are longer and weaker than double bonds, which are longer and weaker than triple bonds. And there is that in terms of a graphic. So weakest down here at the bottom, and then strongest down here, up here at the top, single, double, triple. So let's look at a practice. So calculate the delta H for the reaction. C2H4 plus H2 yields C2H6 using the information in the table above. So that was the information from the previous slide, and the bond enthalpies listed below. So here is your delta H for a carbon-hydrogen single bond and your delta H for a hydrogen-hydrogen single bond. On the AP exam or on class test, you would be given a table of information, a table of data that would allow you to calculate this. All right, so let's go through it. So if you want to try this on your own, go ahead and pause the video now. because I'm just about to go through the answer. So to help you keep everything straight, I'm going to color code the reactants and products for you. So the first thing that I'm going to recommend that you do is to draw the Lewis structures. So here is C2H4. Notice we have a carbon-carbon double bond. H2, of course, is diatomic, and that is a single bond. And then C2H6, we have a carbon-carbon single bond with the hydrogens filling out the octets for carbon. So then if we look at this, we're going to do the bond energy of the reactants minus the products. Again, bonds broken minus bonds formed. So here's our reactants and here's our products. And so now we can start to substitute in here by first thinking about the number and type of each bond. So in the reactants, we've got 1, 2, 3, 4 carbon-hydrogen single bonds. We have 1 carbon-carbon double bond, and we have 1 hydrogen-hydrogen single bond. Now, also recognize we do not have coefficients here, but if we did, we would need to take those into consideration as well. So this is my reactants. Oh, I haven't talked through the products yet, but it's already released for you here. So we have 1, 2, 3, 4, 5, 6 carbon-hydrogen single bonds, and then 1 carbon-carbon single bond. So now we can plug in the data that we have for this. So each carbon-hydrogen bond is going to be 413, so that will go here. My carbon-carbon double bond was on the previous slide. That will substitute in here. Hydrogen-hydrogen is 436. That'll go here. And then over on this side, we're going to have that same number for carbon-hydrogen single bond again, and then a carbon-carbon single bond from the previous slide. So here's all that information substituted in. And all you need to do now is pull out your calculator and let it do the heavy lifting. So then you get you get 2702 minus 2826, which gives you a value of negative 124 kilojoules per mole. So what does this mean? This means that this is an exothermic reaction. The bonds in the reactants contained more energy than the bonds in the products, and this excess energy was released when the products were formed. And so that's what we use bond energies for, and I have seen this question asked both quantitatively and qualitatively on the AP exam. So that's it for this topic. So what should you be able to do with this? Well, you should be able to justify the sign of delta H for a system by comparing the strength of bonds broken in the reactants and formed in the products. You should be able to calculate the delta H for a system using provided bond energies using the equation delta H is equal to the sum of bonds broken, which is the reactants, minus the sum of bonds formed, which is the products. And that's it. And so I will see you soon for our next topic in which we will continue to talk about enthalpy of reaction and how you can calculate that.